When dealing with a transformer that lacks a grounding terminal, it's crucial to ensure proper grounding for safety and code compliance. The primary step is to bond the transformer casing to the main grounding system. This involves creating a reliable connection between the transformer's metal enclosure and the grounding electrode system. This is typically achieved by drilling a hole in the transformer casing, taking care not to damage any internal components, and securely attaching a ground lug. The ground lug then serves as the connection point for a grounding conductor. The grounding conductor must be sized appropriately according to the applicable electrical codes, such as the National Electrical Code, or NEC. The size of the grounding conductor depends on the size of the transformer's secondary conductors. Refer to NEC Table 250.102 for proper sizing. The grounding conductor should then be connected to the grounding electrode system, which typically consists of grounding electrodes such as ground rods, ground plates, or the metal frame of the building if it's effectively grounded. The purpose of this grounding connection is to provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protected devices such as circuit breakers or fuses. Without a proper grounding connection, a fault current may not be sufficient to trip the overcurrent device, leading to a potential shock hazard or fire. Ground fault receptacles, or GFCIs, are designed to protect individuals from electrical shock by detecting small imbalances in current between the hot and neutral conductors. These imbalances can occur when current leaks to ground, such as when someone comes into contact with a live wire. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. On a three-phase high-leg 208/120 system, GFCIs function in the same way as they do on a single-phase system. The GFCI monitors the current flowing through the hot and neutral conductors, and if there is a difference of 5 milliamps or more, the GFCI will trip, interrupting the circuit and preventing electric shock. When installing a GFCI on a three-phase high-leg 208/120 system, it's important to connect the GFCI's line terminals to the transformer's secondary 120 volts conductors. The GFCI's load terminals should be connected to the load devices that you want to protect. The GFCI's ground terminal should be connected to the grounded neutral conductor, the white wire, from the transformer's secondary. It is crucial to ensure that the grounded neutral conductor is properly bonded to the grounding electrode system at the transformer. This connection provides a return path for fault current and allows the GFCI to function correctly. In addition to proper grounding and GFCI protection, it's essential to take additional safety precautions when working with electrical systems. Firstly, ensure that all electrical connections are secure and properly insulated. Loose or poorly insulated connections can create a fire hazard or expose individuals to electric shock. Use appropriate voltage and current rated components throughout the system. Using components that are not rated for the voltage and current of the circuit can lead to overheating, equipment failure, or even a fire. Regularly inspect and maintain the electrical system to identify and correct any potential hazards. Look for signs of damage, such as frayed wires, cracked insulation, or loose connections. Address any issues promptly to prevent them from escalating into more serious problems. When working with three-phase high-leg systems, it's important to be aware of the presence of the high leg, also known as the stinger leg or wild leg. This leg typically has a voltage of approximately 208 volts to ground, which is higher than the 120 volts on the other two legs. Avoid using the high leg for circuits that are only rated for 120 volts, as this can damage equipment and create a safety hazard. Always use a voltmeter to identify the high leg before working on the system. Consulting with a qualified electrician for the installation and maintenance of any electrical system, especially when working with three-phase high leg systems, is strongly recommended. A qualified electrician has the knowledge, skills, and experience to ensure that the system is installed and maintained safely and in accordance with applicable codes and regulations. They can also help you identify and correct any potential hazards before they cause problems. Remember, electricity can be dangerous, and it's always better to be safe than sorry. Always follow proper safety precautions and consult with a qualified electrician if you have any questions or concerns. When installing a transformer, the primary side should be protected by an appropriately sized overcurrent device, such as a circuit breaker or fuse. The size of the overcurrent device should be based on the transformer's primary current rating. Refer to NEC section 450.3 for overcurrent protection requirements. The secondary side of the transformer should also be protected by overcurrent devices. The size of these devices should be based on the transformer's secondary current rating. The overcurrent devices should be located as close as possible to the transformer's secondary terminals. When running conductors from the transformer to the load devices, it's important to use the correct wire size. The wire size should be based on the ampacity of the circuit. Refer to NEC Table 310.16 for conductor ampacity ratings. It's also important to consider voltage drop when selecting wire size. Voltage drop occurs when the voltage at the load device is less than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, use larger conductors or shorten the length of the circuit. When connecting wires to terminals, it's important to use the correct type of connector. Use connectors that are rated for the type of wire being used, such as copper or aluminum. Make sure that the connectors are properly tightened to ensure a secure connection. Loose connections can cause overheating and create a fire hazard. When working with electrical panels, it's important to maintain proper clearance around the panel. The NEC requires a minimum of 36 inches of clear space in front of the panel and 30 inches wide. This clear space allows electricians to safely access the panel for maintenance and repairs. Also, ensure that the electrical panel is properly labeled. Each circuit breaker should be clearly labeled to indicate what it controls. This helps to prevent accidental disconnections and makes it easier to troubleshoot problems. Before working on any electrical equipment, it's important to de-energize the circuit. Turn off the circuit breaker or remove the fuse that supplies power to the equipment. Verify that the circuit is de-energized using a voltage tester. Never assume that a circuit is de-energized just because the switch is turned off. Always use a voltage tester to confirm. When working on energized circuits, use appropriate personal protective equipment, such as insulated gloves and safety glasses. This helps to protect you from electric shock and burns. Avoid working on electrical equipment in wet or damp conditions. Water is a good conductor of electricity, and working in wet conditions increases the risk of electric shock. If you must work in wet conditions, use ground fault circuit interrupters or GFCIs to protect yourself. When installing electrical equipment outdoors, use equipment that is rated for outdoor use. Outdoor equipment is designed to withstand the elements such as rain, snow, and sunlight. Use weatherproof enclosures and fittings to protect electrical connections from moisture. When burying electrical conductors, bury them at the proper depth. The NEC specifies minimum burial depths for different types of conductors. This helps to protect the conductors from damage and prevents them from becoming a shock hazard. When running electrical conductors through walls or floors, protect them with conduit or other approved raceway. Conduit protects the conductors from damage and makes it easier to replace them if necessary. When using flexible cords, use them only for temporary wiring. Flexible cords are not designed for permanent installations. Do not run flexible cords through walls or ceilings, or under carpets or rugs. When splicing wires, use approved splicing methods. Wire nuts are a common method for splicing wires. Make sure that the wire nuts are properly sized for the number and size of the wires being spliced. Always twist the wires together before installing the wire nut. When terminating wires at devices, such as switches and receptacles, use the correct terminals. The terminals are typically marked with the wire color. Connect the black wire to the brass terminal, the white wire to the silver terminal, and the green or bare wire to the green terminal. When installing lighting fixtures, make sure that they are properly supported. Use mounting hardware that is rated for the weight of the fixture. Do not hang lighting fixtures from electrical wires. When using extension cords, use the correct size extension cord for the application. The size of the extension cord should be based on the amperage of the load being supplied. Do not overload extension cords. When using power tools, inspect them before each use. Look for damaged cords, plugs, or housings. Do not use power tools that are damaged. When using ladders, use ladders that are rated for the weight of the user and the equipment being used. Set up the ladder on a level surface and make sure that it is stable before climbing. When working in confined spaces, take extra precautions to protect yourself from electrical hazards. Use ground fault circuit interrupters or GFCIs and make sure that the space is well ventilated. When working near overhead power lines, maintain a safe distance. The NEC specifies minimum clearance distances for working near overhead power lines. Contact with overhead power lines can be fatal. Always be aware of your surroundings when working with electricity. Pay attention to potential hazards and take steps to protect yourself. Electricity is a powerful force, and it should be treated with respect. These are some best practices when dealing with electricity and electrical systems.